Welcome back. Aside from the principle of momentum conservation, the other major result from this chapter is sometimes referred to as the impulse momentum theorem, which is really just another recasting of Newton's second law. And at this point, I'm sure you're getting sick of how everything comes back to Newton's second law, but that's just the reality of this material. That's going to be true for basically the rest of the semester. So let's once again start from F equals ma. And remember, it's a vector equation. You can think of this as being a concise way of writing three simultaneous equations, one along each of the x, y, and z axes. So let's just take a look at one of those axes now. We'll say that the net force, remember, always the net force on an object along the x-axis is mass times, let's see here, mass times the acceleration in the x direction. Acceleration can be written as the time derivative of velocity. And remember what we did previously, we brought the m inside the derivative. Take the time derivative of the product of mass and velocity. This is acceptable as long as the mass is constant. And we recognize this as the definition of momentum. So the alternative statement of Newton's second law, and perhaps a superior way of stating it, is that force is the time derivative of momentum. And maybe you can guess what's happening next. We already integrated this equation once with respect to position in chapter 9, I believe it was, to get the work kinetic energy equation. Now we're going to get something very similar, the impulse momentum equation. So here we go. Draw your worms, choose your integrand. Let's integrate with respect to time on both sides. And we'll make it a definite integral, integrate from t initial to t final. Of course, you could call it T1 to T2, whatever notation you prefer. And once again, what happens if you first differentiate some quantity with respect to time and then integrate with respect to time? Those operations undo each other. Many of you don't need to see this connection, but if the derivative with respect to x of capital F of x is something we call lowercase f, then the antiderivative, or the integral of lowercase f, is capital F plus some constant of integration. So here, if we want to draw a comparison with what we're doing right now, big F, okay, Zoom cut out for a moment. It's been doing that quite a bit lately, so I'm just going to repeat the last couple sentences. I don't know what got dropped. I was making a comparison between what we're doing now and the fundamental theorem of calculus, as you probably learned it in your math class. So I'd like to identify the big F and lowercase f in what we're doing presently. And it's a little confusing because over here we're using big F for force, but that's really not the same as the big F over here. Here, the capital F, let me put an arrow, it's because they're not really equal, would be the x momentum. And instead of a derivative with respect to x, I'm talking about a derivative with respect to time. So lowercase f of x goes to dp dt. Okay, so the derivative of this is this, and I'm talking about a derivative with respect to time. The derivative of a piece of x is dp dt. And so the antiderivative of dp dt is p plus your arbitrary constant, but since we're doing a definite integral, that goes away. Okay, it's not really necessary to make those connections, but I was trying to convince you that the antiderivative is simply p. So the integral of force over time between these two times, the antiderivative of dp dt with respect to t is just p, and we evaluate at upper and lower limits. And I need a good name for the momentum at time t final and the momentum at time t initial. And of course, the obvious choice would be p final and p initial. So let's rewrite that one more time. Integral of force with respect to time would be p final x minus p initial sub x. And I'm going to put a big box around that because that's really the result that we were working towards. Again, I've said it many times in the last dozen videos or so, there's no new physics here. This is F equals ma after it's been integrated with respect to time. And now let's assign some names to these quantities. The appropriate name for this is obvious. It's final minus initial. So let's call that the change in the x component of momentum. Remember, momentum is a vector. Right now, we're looking at one component of that vector. And then this quantity, force times time, well, what are the units here? We've got newtons and seconds. So the units would be Newton seconds, but evidently that's the same as the units of momentum. Remember, anytime you equate two quantities, they have to have the same units, with the exception of a unit conversion, but that's not what we're doing here. So the units of momentum evidently are Newton seconds. You can also write them as mass times velocity is kilogram meters per second. These are the same. And the name for this quantity is impulse. And we use a capital letter J. That's pretty universal. Most books use a capital letter J for impulse. We avoid I because it's already reserved for current in circuits or the square root of -1. Or it's difficult to just tell the difference between I and J with typesetting. So there it is. This is called impulse. It is the integrated version or form of Newton's second law. Force gives the rate at which momentum is changing. But you can also look at this and recognize that how do you change something's momentum? You apply a force to it. That's the differential way of looking at it, where your time interval is infinitesimal. If you integrate between two times separated by a finite interval, you get this. A finite change in momentum is impulse. So how do you change something's momentum? You deliver an impulse to it, or you apply an impulse. What is an impulse? It's a force applied in time. So we'll look at this graphically, but seriously, make note here that we're talking about the components of a vector. The full vector form of this equation, and you could just repeat this process along the y and z axes and summarize the whole thing by saying impulse, the vector, is change in momentum, the vector. Okay, so how would you actually calculate impulse? There's two ways to do it. If you knew the final and initial momenta, you would just subtract the two vectors, and that vector is the impulse. That's what this equation is saying, right? If you know the initial momentum vector and the final momentum vector, just subtract the two vectors. That vector is the impulse vector. Or if you happen to know exactly how the force depends on time, then you could just integrate that force and call that impulse. Either way, you get the same result. So which method you choose is going to depend on the problem. It's going to depend on which information you have. And before we look at an example here and talk about the graphical interpretation, I'd like you to compare that with a previous result compared to, well, instead of saying that impulse gives a change in momentum, how about work gives a change in, you guessed it, kinetic energy? This analogy should help you remember both equations, really. In each case, you're looking at the change in some quantity associated with motion, with mass and velocity. And over here, this quantity is an integral. So I'm going to emphasize the differences here. This is a vector equation. This is a scalar equation. How do we calculate impulse? It's the integral of force in time. Now, do you see how what we're really doing is we're taking a vector and scaling it by this tiny little quantity dt. dt is a scalar. And then we're adding up all those vectors. That's what an integral is, right? So this is the sum of an infinite number of vectors, but each vector is infinitesimally short. Like if this was 10 newtons and then you multiplied it by, remember dt doesn't actually have a value, but think of it like a billionth, 0.000001, you get the idea. Then that would scale your vector down to something really short, but you're adding up an infinite number of them. So the idea is this comes out to be some finite quantity, which we call impulse. But it is a vector. Now down here, the work integral was a little different. We took the force vector and dotted it with displacement. So this dot product is a scalar. It's an infinitesimal scalar, but then we add up an infinite number of those to get some finite scalar. So there are some differences between the two. One is a vector equation, one is a scalar equation. And the definitions of these quantities are simply different. But in each case, it gives you the change in some quantity having to do with motion. It's easy to confuse kinetic energy and momentum because in one dimension, they're so similar. Kinetic energy is 1/2 m times the square of the speed, and momentum is mass times speed. So, it's been so long now since I learned all this stuff. Sometimes I still wonder, what's the fundamental significance of this? Why do we even have two different quantities and they both involve the same variables, mass and speed? Do we need them both? Well, it just depends on what you're being asked to do. And that'll become more clear as you do problems. But if the information that you have at your disposal is something like force and time interval, then you would use this equation. I'm not specifying a subscript because I'm just leaving the axis open-ended. But if you've got force and time intervals at your disposal, then you probably want to deal with impulse and momentum. But if instead you know something about the force and how it depends on position, then you would probably want to use work and kinetic energy. Of course, in chapter 11, you don't have to do any guesswork because you know what this chapter is about. Go with impulse, momentum. So the graphical interpretation. Let's go with how about a car crashing into a wall? I can't draw. That doesn't look anything like a car. Maybe a Batmobile. Okay, there's your antenna. And this thing is about to smash into the wall. And of course, the front end's going to crumple. And while it's crashing into the wall, there's going to be a large force that the wall exerts to the right on the car. So if I set up my coordinate system this way, and I label this force F sub x, you can imagine that when the bumper first touches the wall, there's not a very large force yet. The car has to begin to crumple before you develop this large force. It's kind of like if you took a racquetball or a tennis ball and you put it in your hand. If you squeeze lightly, it doesn't compress by much. But in order to get it to compress a lot, you have to squeeze really hard. So the more compressed this car gets, the larger the force is between the wall and the car. And if you were to graph that force in time, you might expect it to look something like this. I've just drawn these details, the bumpiness somewhat arbitrarily, but it's pretty clear that there won't be any force until the car makes contact. I could call that T initial. And then it's going to peak somewhere in time. And then once the car has bounced back and lost contact with the wall, the force will drop back down to 0. And usually in most problems, we're not actually aware of the detailed shape here. We don't really know how the force depends on time exactly. Now, in a physics laboratory, you can hook up force sensors to things and have a computer sample data, every 100th of a second, measure the force and store that data in the computer and then graph it. So you could do that in a physics lab, but in real life, usually we don't know what the force was in time. But we can still extract some information about this curve. And we do that using what I think you could call the fundamental theorem for integrals. Let's not worry so much about the math language, but you can imagine that there's got to be some rectangle with a base equal to the time interval here and a height such that, maybe it's right here. So I've tried to choose the height of this rectangle so that the area under the rectangle is the same as the area under the curve. Let me shade in the area under the curve. So maybe I didn't do a great job, but if you look, this rectangle is missing this extra hump here, but it does have these pieces. So very roughly, these pieces would have to add up to this piece. I didn't do it great. But if you can find that rectangle, the rectangle that has the same area as the area under the force versus time curve, then by definition, the height of that rectangle is called the average force for the time interval. And if you want to look back at your calculus book, you'll see that that comes from the mean value theorem for integrals. But that is the meaning of average force. It's the height of the it's the height of the rectangle with the same area as the force versus time curve. So I can go back to this equation, the impulse momentum equation, right? Impulse along the x-axis is the change in momentum along the x-axis. And remember, graphically, the integral gives you the area. That's what this expression is, right? It's the area under the black curve. So I might as well replace that by an expression for the area of the rectangle. Let's call the time interval delta t, and then I can just replace this by f average delta t. And now you see one thing that this equation allows us to do. If we happen to know the mass of the object, like the car that I was talking about, if we know the mass of this car, maybe it's 1,500 kilograms, and you know its initial and final velocities, because that's often very easy to estimate. We know how fast a car is going before it strikes something, either from video or from somebody having looked at the speedometer, or we can at least estimate it. So we can easily calculate the change in momentum. And the time interval can also be estimated, and that allows us to find the average force. Again, we're just using F. Okay, Zoom cut out again, just as I was reminding you once again that what we're really doing here is just applying F equals ma in integrated form. So maybe that's the universe trying to tell me something. I've said that enough times. Okay, I think we should apply this to a problem, but I can also call this the impulse momentum equation. Some books say impulse momentum theorem. I think it's unnecessary to call it a theorem because there's really no new content here. All we've done is integrate F equals ma. And now we're prepared to solve a very simple problem from your homework. Number 12, this is about gliders on an air track. So let me pull up a couple seconds from a YouTube video. Here are two gliders which are going to collide, but the problem that we're looking at actually involves a single glider which is moving to the left. So as you watch this, focus your attention on the right one, because in the problem, this glider which is moving to the left would not actually strike this second glider. It would make it all the way to the end of the track where there's a spring, and it's supposed to bounce off the spring and then move back to the right. But the spring has some sort of force sensor attached so that we can collect data and actually plot the force versus time. And we also would have analyzed this in Tracker to get the velocity versus time. So here's the little motion. So now you know what we're talking about in the problem. Here are the graphs as they're presented in the problem at the end of the chapter. First, they're telling us how the velocity depends on time, and notice they're specifying the x component of velocity. The velocity begins negative. That's what tells us that the glider is moving to the left, just like the one that I pointed out in the video. And then the absolute value of the velocity is decreasing until we get to here. At this point, the velocity is 0. That's when we know that the speed is 0. So in other words, this glider came in from the right. It was heading left. It slowed down. It came to a stop. And then it picked up speed to the right because over here, the velocity is positive. And at the end, it's got a constant velocity, which means it's not accelerating, which indicates there's no force. And that means that it's lost contact with the spring. Now they're also showing us how the contact force between the spring and the glider goes from nothing when they're not touching, and then it turns on, so to speak, reaches a peak, and then drops back down. And they've actually drawn it as a triangle. These are basically straight line segments in the graph at the end of the chapter. And looking at this just now, I noticed something that I had not noticed before because I've seen this problem before. There's really an inconsistency here. If we look at the velocity versus time graph, would you agree that between basically this time and this time, well, maybe this time, the slope doesn't change. See how there's a constant slope here? Well, the slope of velocity is acceleration. Acceleration is the derivative of velocity with respect to time. We know that's the slope of the tangent line. So if the acceleration is constant in here, that would indicate that the force on the glider is also constant, and they have not reflected that in this graph. Do you see how this force is always changing? Sure, the slope is constant, but that's not the interpretation that's correct. The force is always increasing or decreasing. To actually reflect the fact that there's a constant acceleration, they should have drawn the force so that it increases and then plateaus and then drops back down. And that plateau of constant force would have corresponded with the constant slope. So a little goof on the part of whoever wrote this problem, but that's no big deal. Now, a moment ago, I was talking about how you can replace the area under the F versus T curve with, I've already thrown that out, looks like, yeah, with an equivalent rectangle. Here, we don't actually need to do that because a triangle is a very simple shape for which we know the area, 1/2 base times height. So let's use that to calculate delta t. That's what they're asking for. So given all the information in the graph and the fact that the glider has a mass, let's see, we're told that the glider has a mass of 600 grams. We're going to need that. Once we find the change in momentum, we'll divide out the mass to get velocity, I suppose, or do that same process inside out. You'll see, because we actually know the final and initial velocities here. Find delta t. Okay. First of all, is this a conservation of momentum problem? We are in chapter 11, and momentum conservation is one of the major themes in this chapter, but you can only make the case that momentum is a conserved quantity if there's no force on your system. But of course there's a force on this system. That's the whole point. So this is not a momentum conservation problem. This is an F equals ma problem dressed up in the clothes, the integrated clothes. This sentence doesn't make any sense. Cast in this new form, the impulse momentum equation. So if you don't see immediately how to start, just write that equation down. Just go ahead and observe that the x component of the impulse should be the change in the x momentum. And now recall that impulse, by definition, is the definite integral of the x component of force in time. And I'll point out, whether it's you throwing a baseball, you hitting a baseball with a bat, you tackling somebody, how do you, I'm thinking football here, how do you change something's momentum? You have to apply a force, and you have to do that for some time interval. You could increase the impulse by either pushing harder or pushing for a longer time. Everybody knows this, right? We all know this. That's perhaps one reason why pitchers tend to be taller people with longer arms, because they're able to push on the ball for a longer time. Or maybe you could say through a longer distance, but then you're talking about work. Okay. Now, here's where we recognize that this integral is the area. I can just replace that with our formula from geometry. That's going to be 1/2 base times height. Well, the base is the time interval that we're trying to calculate. This is 1/2 here. And the height is what I'll call F max. It's the max or the peak value reached by the force. So 1/2 base times height is 1/2 delta t F max. And for constant mass, you can write the change in momentum as mass times delta V. So it may not look like it, but this is F equals ma. In fact, to convince you of that, off to the side here, check it out. I'm going to move some stuff around. Well, I'll do it here. I'll say this is the same as Fx average times delta t equals m delta v. Impulse is change in momentum, but let's solve for F average, and I would have m times delta v over delta t. All I did was move some stuff around, but don't you now recognize F equals ma, rate of change of velocity? If it feels like we're going around in circles here, it's because we are. Let's solve for delta t now. That would be 2 times the change in momentum. M delta v is the change in momentum. Double that and divide by the max force, and that would give you the time interval. So we can plug in numbers now. 600 grams is 0.6 kilograms. And then for the change in velocity, let's refer to the graph. Well, the final velocity, remember it's coming in from the left and it gets bounced back to the right. The initial velocity was -3. The final velocity is +3 in SI units. So that would be 3 minus, and here you must be careful with signs. Final minus initial is 3 minus -3. You can't just subtract speeds. That's no good. Because if you were subtracting the speed, you would say 3 minus 3 is 0. And you would find a delta t of 0. That makes no sense. So you must account for signs. And we're dividing by that max force of 36 newtons. And we're expecting a small time. It shouldn't take long for this thing to bounce off of the spring. So here I've got a 6 times 2 times 0.6 divided by 36 newtons. And I get 2/10 of a second. Okay, so if you sense that it's an impulse momentum problem, this would be your starting point. While we're here, I'd like to look at one other problem that requires the principle of momentum conservation. So this is back to the topic from the previous video. We don't need the impulse momentum theorem for this problem. It's kind of a fun one because there's a shortcut you can take, which in hindsight is rather obvious, but the solutions manual has a more detailed and really unnecessary solution. So this is number 17, and the premise is the following. There are 3 railroad cars. They're already coupled together, and they're moving at some shared velocity v0. But then there's this 4th car behind them that's catching up because it's going twice as fast as these are. So this cart's going to bang into the first 3 and couple together. So all 4 of them will then be rolling together. And all the while, there's a 5th car which is just chilling on the tracks, no velocity at all. And eventually, these 4 will slam into the 5th. All 5 of them will be coupled together, and we are supposed to find the common final velocity. The book also tells us that each of these cars has the same mass. So let me just use the letter M for the mass of each car. All the same. We're not actually told what that mass is. We're not given the initial velocity. So we're supposed to obviously find the final velocity in terms of these unspecified quantities M and V0. Okay, now your first reaction may be, well, how are we supposed to proceed here? If this was chapter 6, we would be totally lost because the only tool we had was F equals ma. So we couldn't even begin to describe the acceleration of any of these carts during a collision unless we knew the nature of the force. We would need to know the details of how the force depended on time if we had any hope of calculating the acceleration and then integrating to find the change in velocity. That's the difficulty before this chapter. You need to know how force depends on time in order to integrate acceleration. But what we can recognize here is these are train cars, firstly, and the whole idea with a railroad car is that there's supposed to be very little rolling friction between the metal wheels and the metal track. Now you can look up, you can go back to the chapter, probably chapter 6, and look up the table of coefficients of friction. And when it comes to rolling friction, you can't get much better than steel on steel. I don't know if we're actually talking about steel for most railroad cars, but it's got to be something similar. So we can just ignore the rolling friction. Ignore rolling friction. And we can also ignore air drag. Now, realistically, if these train cars were even going at like 30 miles per hour, there's going to be significant air drag. And that means there would be an outside force. So let me draw a bubble around this whole thing. This is my system, the combined system of all 5 railroad cars. Now, when these bang into each other, there will be forces between them, but those are internal forces. As far as outside forces go, I conclude that the x component of outside forces is 0. Yes, the ground is pushing up on the system. Yes, gravity is pulling down, but those are vertical forces. Those have nothing to do with x momentum. So it should be that the total x momentum of this system, oops, not 0, constant. The time derivative would be 0, because remember, that's what Newton's second law says, right? Force is time derivative of momentum. If there's no force, there's no change in momentum. In other words, the momentum is constant. So what your solutions manual does is to break this into two steps. They first look at the collision between these three and the rear car to find their shared velocity, v, before colliding with the fifth car. Once they find that velocity, then they once again invoke the conservation of momentum to find the shared velocity at the end. But I'm not even going to bother writing this out, but let's just loosely refer to this as time 1, time 2, and time 3. If capital P, the total momentum, really is a constant, then capital P at time 1 is capital P at time 2 is the same as capital P at time 3. There's no need to do this and then this. Just jump straight from the initial state to the final state. What could be easier than that? So the total momentum at time 1 needs to equal the total momentum at time 3. Well, what do we have in the beginning? This car's momentum is 0. The total mass here would be 3m, 3 cars moving at speed v0, plus a single car, that's mass m, moving at speed 2v0. All right, so there's the two separate momentum contributions. At the end, all 5 of them are stuck together. That's a mass of 5m moving at some unknown speed vf. And look how trivial this problem is now. The m's divide out. We've got 3v0, 2v0, that's 5v0 equals 5v final. Evidently, the final speed is the same as the original speed shared by these 3. Trivial problem. Of course, in a real life scenario, this would not allow you to accurately, if you had a speedometer that could determine the speed to the nearest tenth of a mile per hour, the actual speed would be a little different than this prediction because we have not accounted for rolling friction, air drag, and perhaps even some other effects that are escaping me. But the point being, the total momentum of the system would not really be conserved. Some of that momentum would be changed or removed, I suppose you could say, by those outside forces, dissipative forces, air drag and rolling friction.